Greetings, respected faculty members. Today, our team will be presenting our work on Tutorial 5, the windshield wiper mechanism, as a part of Mechanism Sessional. Here is the structure of our presentation. We will begin with the problem statement, followed by Grashof criteria, displacement analysis, velocity analysis, and finally, graphical synthesis. This was the project completed by our team of three. Myself, Varun Nikam, 23ME 10095, Pawan Paune, 23ME 30038, and Harshvardhan Kumkar, 23MF 10017. The objective of this work is to synthesize a windshield wiper mechanism that provides a smooth oscillatory motion without a quick return effect. We also simulate the mechanism to determine three things: the total wiping angle and area wiped, the velocity and acceleration variation of the blade for constant motor speed, and the torque required at the motor neglecting the dynamic forces. The geometry provided to us was a 4-bar linkage, and we also used it for both graphical and simulation analysis. Now I'll hand over to Harshvardhan. He'll explain the part of kinematic analysis.
In this slide, we'll discuss the Grashof criteria, which helps to determine whether a link in a 4-bar mechanism can complete a full rotation or not. When the sum of the shortest and longest link is equal to or less than the sum of other two, the shortest link becomes the crank. This principle is applied in wiper mechanisms, where the motor-driven link rotates continuously while the wiper arm rocks back and forth. By fixing different links, we get different inversions of the mechanism. When a link adjacent to the shortest is fixed, we obtain the crank rocker configuration commonly used in windshield wipers. The mechanism operates within a single assembly mode, meaning it cannot switch sides during motion. In non-Grashof mechanisms, however, all links simply rock, forming a double rocker system. Now, as we can see, the link between angle theta 2 and output angle theta 4 is therefore being provided by the displacement analysis. So we will look into this part of the analysis of kinematic mechanism. As you can see in the figure, the link lengths of the above kinematic diagram are AB, which is equal to L1, BC equals L2, CD equals L3, and AD equals L4, where AD is the ground and DE is equal to L0, which is the extension, and links CD to the mechanism with the wiper as a result. We can choose A as our origin with AD as the x-axis and y-axis perpendicular to it. Now with respect to A, we can find the coordinates of point B and C, and we can see the coordinates of B are L2 cos theta 2, L2 sin theta 2, and the coordinates of C are L1 cos theta 4, L1 plus L4 cos theta 4, L4 sin theta 4. As we already know B and C, we can find the distance between them using the Euclidean distance formula. So we get the distance between B and C as L1 plus L4 cos theta 4 minus L2 cos theta 2 whole square plus L4 sin theta 4 minus L2 sin theta 2 whole square whole under root. Now as we all have these equations, we can obtain the length L3 with respect to theta 4 using the trigonometric equations and half angle relations as shown in the above slide. We can find the values of theta 4 and all the coordinates of all other points that are used in the mechanism. Finally, we get the theta 4 as twice of the tan inverse minus a plus minus root under a square plus b square minus c square over b plus c. A is nothing but sine theta 2 and b is cos theta 2 minus L1 by L2. Same way, we can get value of tan theta 3 as L4 sin theta 4 minus L2 sin theta 2 over L1 plus L4 cos theta 4 minus L2 cos theta 2. Now I will be explaining velocity and acceleration analysis. So the velocity analysis provides a relation between input velocity and angular velocity. Now from Arnold Kennedy theorem, we know that if three bodies are in relative motion, they must have collinear ICs. As L2, L1 and L4 are in relative motion, I13 must lie on I14 and I34. Similarly, L2, L3 and L4 are in relative motion. Therefore, I13 must lie on I23 and I12. Thus, we can find that I13 is at the point X. Now we have obtained the displacement equation where A, B and C are function of length and angles. The displacement equation obtained is a relation equation which relates the magnitude of vector L2 to L4 with the length L3 upon differentiating the equation with respect to time, we get the velocity equation in terms of Jacobi, which is denoted as J. Here we can see that theta 4 dot is equal to L2 by L4 multiplied by L4 sine theta 2 minus theta 4 plus L1 sine theta 2 whole upon L2 sine theta 2 minus theta 4 plus L1 sine theta 4 into theta 2 dot, which is represented as Jacobi. So theta 4 dot is Jacobi times of theta 2 dot. So theta 4 dot is I times theta 2 dot. Differentiating further, we get the acceleration analysis, which is theta 4 double dot, which is equal to del J upon del theta 2 plus del J upon del theta 4 whole bracket into theta 2 dot whole square plus del theta 2 double dot. Now we have the equations for del J, del theta 2, del J, del theta 4 and A, B and C. Therefore, we can get the acceleration as well as the velocity.
Now I'll demonstrate the graphical synthesis of our windscreen wiper mechanism. Here you can see the graphical construction. I have created using a scale of 1 cm is equal to 4 cm. All the link lengths are taken exactly as given in the Sessional 2 assignment, and I've also prepared a scaled figure to support the calculation. In the synthesis, we have taken O4 as the fixed pivot, and using O4C1 as the radius, we draw the arc C1C2. This arc represents the path traced by the tip of wiper blade. The radius here is 300 mm, which becomes an important parameter for calculating the wiper area. From the graphical analysis, we obtain the swipe angle beta is equal to 63.6 degree. With this angle, we calculate the arc length using the formula arc length is equal to beta by 360 degree into 2 pi r, which results in 33.31 centimeter. To estimate the total wiped area by the blade, we multiply this arc length by the effective blade length E1 F1. From this area of the swept region comes out to be approximately 666.2 centimeters square. This graphical approach helps us clearly visualize the mechanism's motion and accurately determine the wiped area of the windscreen. Finally, the part of simulation using the SolidWorks will be explained by Pawan.
So this is our windscreen wiper mechanism that we created using SolidWorks. So we will start with a fully defined 2D sketch on the front plane, a closed polygon with all dimension, 50 mm vertical, 80 mm base, 30-degree and 60-degree angles. Now we will enter motion study. A path mate is applied through which we will show the demonstration of this mechanism. Was the mechanism, the link will rotate about the fixed origin, sliding along the 30-degree path. The timeline shows a smooth 5-degree second cycle. This demonstrates kinematic constraint path following as cyclic motion in SolidWorks. My team would like to express our heartfelt gratitude to our project guide for his guidance, support, and valuable feedback throughout this work. We also thank our teaching assistants for their cooperation and resources that made this project possible. So this is conclusion of our windscreen wiper mechanism that exemplifies kinematic principles, particularly the Grashof criterion for ensuring a crank in 4R chains. By satisfying L minimum plus L maximum less than equal to P plus Q, the input link rotates completely, driving the oscillating wiper. Analyze velocity and synthesis as shown in the project diagrams demonstrate practical applications. This project highlights why complete rotatability is vital in motor-driven mechanism, as seen in examples like box loaders or power saws, and addresses inversions and assembly modes for robust design. Thank you for reviewing our work.